Section 18 of The Science History of the Universe, Volume 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Marianne. The Science History of the Universe, Volume 2, edited by Francis Rolt-Wheeler. Geology, Chapter 9, Destructive Agencies, Part 2. Having learned the general character of river erosion, a few concrete examples will be interesting. A particularly valuable case is that of the little river Simeto in Sicily, since the history of its gorge is so well known. In 1603 a great lava flood from Etna was poured out across the course of the stream and, when cold, solidified into a barrier of the hardest rock. When Sir Charles Lyell visited the spot in 1828, he found that in a little more than 2 centuries the stream had cut a gorge through this barrier, of 40 to 50 feet deep and varying in width from 50 to several hundred feet. The lava which had thus been trenched is not porous or slaggy, but homogeneous, dense, and very hard. In northern parts of the United States, the great ice sheet brought down with it vast quantities of drift that filled up the channels of many streams and quite revolutionized the drainage of certain districts. Since that time the displaced streams have cut out new channels for themselves. Au Sable Chasm, New York, is an example of these geologically modern river gorges, the atmosphere not having had time to widen it. The Niagara is an exceptional case, the gorge being cut not only by the direct abrasion of the running water, but also by the action of the spray and frost at the falls. In the ravine, the upper rock is a hard, massive limestone, which is underlaid by a soft clay shale. The latter is continually disintegrated by the spray of the cataract and by the severe winter frosts undermining the limestone, which, when no longer able to bear its own weight, breaks off in tabular masses. Thus the falls are steadily receding, leaving behind them a gorge, which is deepened by the river and especially by the plunging masses of water at the foot of the cataract. One of the most remarkable known examples of river erosion is seen in the canyons of the Colorado. The Grand Canyon is over 200 miles long and from 4,000 to 6,500 feet deep, with precipitous walls. It is extremely probable that the river has been rendered able to cut to such profound depths by the gradual uplifting of the whole region, which is now a lofty plateau, in places more than 8,000 feet above the sea. The scope of the transporting power of running water is dependent upon the velocity of the current. If the rapidity of a stream be doubled, it can carry 64 times as much as before, being as the 6th power. The destructiveness of sudden and violent floods is thus explained. In the terrible flood which overwhelmed Johnstown, Pennsylvania, in 1889, great locomotives and massive iron bridges were swept off, it is hardly an exaggeration to say, like straws, and huge boulders carried along like pebbles. The quantity of material which rivers are continually sweeping into the sea is enormously great. Each year the Mississippi carries into the Gulf of Mexico nearly 7,500,000,000 cubic feet of solid sediment, either in suspension or pushed along the bottom, an amount sufficient to cover 1 square mile to a depth of 268 feet. In addition to this is the quantity brought down in solution, which is estimated at 2,850,000,000 cubic feet annually. And yet this astounding volume only represents a lowering of the surface of the entire drainage at the rate of 1 foot in 4,920 years, for it must be remembered that North America's great river drains 1,325,000 square miles. In addition to the destructive agencies of the atmosphere and of running water, the sea plays a large part. Upon the coastline, whether it be rock or beach, the waves dash interminably, not only possessing the force which has been imparted to them by the wind, but also from the tension of oceanic current and the tides. According to observations made for the Scotch Lighthouse Board, the average wave pressure on the coast of Scotland is for the 5 summer months 611 pounds per square foot, and for the 6 winter months 2,086 pounds. These are average figures, and are greatly exceeded in storms, when the force of the breakers often rises to many tons per square foot. The gentlest movements have some grinding action among the sands, while the heaviest may dislodge and move along, up the shores, rocks many tons in weight. Niagara wastes its power by falling into an abyss of waters, but in the case of the waves the rocks are barred anew with each successive plunge. The waters are often loaded with gravel and sand when they strike, and thus carry on abrasion. Cliffs are undermined, rocks are worn to pebbles and sand, and, through mutual friction, sand is ground to the finest powder. Rocky headlands on windward coasts are especially exposed to wear, since they are open to the battering force from different directions. The coast of Yorkshire in England is washed away at an average rate of nearly 7 feet per annum. The island of Heligoland, near the German coast, has suffered great loss from the attacks of the sea within historic times. The small eastern island was cut off from the larger island, Heligoland proper, by a great storm in 1720. At Long Branch, New Jersey, the sandy bluffs must be artificially protected against the attacks of the sea, yet in spite of such protection, almost every severe gale does considerable damage. Sandy coasts which are low-lying and flat often suffer less from the inroads of the sea than rocky and precipitous ones, but even such coasts may, however, be rapidly cut back. Limestone coasts suffer from solution by sea water and are characterized by long caverns and tunnels, though sea caves are worn by the surf in all classes of rocks. Of far less influence are the lakes, which indeed are to be regarded as merely temporary bodies of water, and which, either by being filled up or by the gradual wearing away of a barrier which obstructs them, will disappear. In the Great Lakes there are small tides and small breakers, which in all details follow the nature of marine destruction, but on a far smaller scale. It is otherwise, however, with snow and ice. Snow in the form of avalanches, which frequently bring down with them masses of earth, and ice in the form of glaciers. A glacier, says Scott, is a stream of ice which flows as if it were a very tough and viscous fluid, and does not merely glide down a slope, as snow glides from the roof of a house. Their contribution to the sum total of rock destruction and reconstruction is relatively small, but their former extension has a wide bearing upon some of the most far-reaching of cosmical problems. The height in the Alps of the snow line, or that below which the snow annually precipitated melts during the year, is about 8,400 feet on the north side of the Alps and about 8,800 feet on the south side, and the glacier may descend below this line 5,000 feet or more. Though starting where all is white and barren, it passes by regions of alpine flowers, and often continues down to a country of gardens and human dwellings before its course is ended. Thus the Glacier de Bois, an upper portion of which is called the Mer de Glace, rises in Mont Blanc and other neighboring peaks, and terminates, like several other glaciers, in the vale of Chamonix. In a similar manner, two great glaciers descend from the heights of the Pyrenees Alps to the Grindelwald Valley, just south of Interlaken. Snow is made up of minute hexagonal crystals of ice, which are intimately mixed with air and thus separated from one another. Ice is composed of the same kind of crystals as is snow, but they are in contact with one another, not separated by air. To convert snow into ice it is only necessary to expel the air and bring the crystals into contact, for which pressure alone is not ordinarily sufficient. The first step in the transformation is the partial melting of the upper layers of snow. The water thus formed trickles down into the snow beneath, expelling much of the air. This underling snow still has a temperature much below the freezing point, and the percolating water is soon refrozen into little spherules of ice. This substance, midway between snow and ice, is called neve. The air, which is now in the form of discrete bubbles, is largely expelled by the increasing pressure of the overlaying snow masses, which are continually added to by renewed falls, and the neve is thus converted into ice. A glacier moves in much the same way as a river, but at a very much slower rate. The middle portion moves faster than the sides, because the latter are retarded by the friction of the banks, and, for the same reason, the top moves faster than the bottom. While behaving like a plastic substance under pressure, ice yields readily to tension, and even a slight change in the slope of the bed will cause a great transverse crack or crevice to form. Marginal crevices are formed along the sides of the glacier, and are due to the more swiftly moving middle pulling away from the retarded sides. The rate of glacier movement depends upon the snow supply, upon the slope of the ground, and the temperature of the season. The great stream of ice which enters Glacier Bay in Alaska has a summer velocity of 70 feet per day in the middle. Newly formed glaciers remove the soil, talus, and other loose material from the surface, and then the bare rocks are eroded by a double process. The joint blocks are torn away by the advancing ice, an operation which is much facilitated by the continual liquefaction and relegation of the ice at the bottom of the glacier, owing to changes of pressure, for it must be remembered that the melting point of ice varies with the pressure, and this is continually changing due to the motion of the glacier and inequalities of the bed, and in this manner the joint blocks of the bedrock are loosened. The bottom of the glacier is a mass of ice mingled with rocks, pebbles, boulders, sand, and debris of all sizes, and by their means the rock bed is worn down, smoothed, polished, and scored with parallel marks in a fashion which forms the unmistakable autograph of the glacier. In the lower part of a glacier, says Dana, the several moraines generally lose their distinctness through the melting of the ice and also by reason of the fact that the glacier is generally compressed in its lower part to a width very much less than the aggregate width of its tributaries. The surface of the glacier accordingly often becomes covered with earth and stones for the greater part of its breadth. The bluff of ice which forms at the foot of a glacier is often a dirty mass, scarcely revealing superficially its real nature. Besides the superficial moraines, a glacier also gathers rock material from the bottom over which it moves. The disintegrated and decomposed rock is mostly scraped from the surface, masses of rock are torn off from jointed ledges, and soft rocks in the path of the glacier are deeply abraded. The final melting leaves all the earth and stones in unstratified heaps or deposits, which may be further transported, abraded, and deposited by the stream that flows from the glacier. The mass of such deposits dropped at the foot of a glacier is called the terminal moraine. River, lake, and coast ice also transport material. When a glacier enters the sea, it plows along the bottom until the buoyant power of the water breaks off great fragments of it, which float away as icebergs. These are often of gigantic size, veritable islands of ice, and huge as they appear, only about 1/9 of their bulk is above the water. As icebergs are derived from glaciers, they carry away whatever debris the parent glacier had upon or within it, and, wherever they melt, they drop all to the ocean's bottom. The sea about the Newfoundland banks is one of the regions of melting icebergs, and there is no doubt that vast submarine accumulations of such material have been made there by this means. Organic forces also play a part. Seeds germinating in the crevices of rocks, or the roots of trees which invade such crevices from above, wedge the rocks apart with the same irresistible power as is displayed by frost, and often large areas of rock are thus most effectively broken up. Many marine animals bore into rocks, even the hardest, and cause them to crumble, and on the land great numbers of animals continually bore and tunnel through the soil, allowing a freer access of air and water. In the tropics the soil is fairly alive with the multitude of burrowers. Earthworms are among the most important agents in work of this kind. The worms swallow quantities of earth for the sake of the organic material which it contains, and grind it exceedingly fine in their muscular gizzards. This ground up soil is always deposited on the surface in the form of the coiled worm castings so abundant in grassy places. In England material thus yearly brought to the surface varies from 7 to 18 tons per acre, which means an average annual addition of 1/10 to 1/6 of an inch. In the tropics ants and termites, so-called white ants, are even more active than worms in tunneling the soil, and in many semi-arid plains burrowing mammals in incredible multitudes are continually working over the soil to great depths, as in the prairie dog villages of our western plains. The occasional heavy rains thus penetrate to depths which could not otherwise be reached. The immense influence exerted by man upon the changing condition of physical geography has been summarized by Geikie. The great geologist regards him as a factor antagonistic to the methods and designs of nature. Not content with gathering the fruits and capturing the animals she has offered for his subsistence, he says, man has, with advancing civilization, engaged in a contest to subdue the earth and possess it. His warfare, indeed, has often been a blind one, successful for the moment, but leading to sure and sad disaster. He has, for instance, stripped off the woodland from many a region of hill and mountain, gaining his immediate object in the possession of their stores of timber, but thereby laying bare the slopes to parching droughts and fierce rains. Countries once rich in beauty and plenteous in all that was needful for his support are now burnt and barren, or washed bare of their soil. It is only in comparatively recent years that he has learned the truth of the aphorism, Homo naturae minister et interpres. Human interference affects meteorological conditions by removing forests and laying bare to the sun and winds areas which were previously kept cool and damp under trees, or which, lying on the lee side, were protected from tempests. By drainage, the effect of this operation being to remove rapidly the discharged rainfall, to raise the temperature of the soil, to lessen the evaporation and thereby diminish the rainfall and somewhat increase the general temperature of the country. By the other processes of agriculture, such as the transformation of moor and bog into cultivated land, and the clothing of bare hillsides with green crops or plantations of coniferous and hardwood trees. By increasing or diminishing the rainfall, man directly affects the circulation of water over the land. By the drainage operations, which cause the rain to run off more rapidly than before, he increases floods in rivers. By wells, bores, mines, or other subterranean works, he interferes with underground waters, and consequently with the discharge of springs. By embanking rivers, he confines them to narrow channels, enabling them to carry their sediment farther seaward, and in 1,000 other ways his influence is felt. End of chapter 9.